Kia ora, Year 12 and 13. This is the vectors question from last Thursday's test, and it's got 3 parts to it. In the first part, we have to calculate the acute angle between lines AB and CD. In the second part, we have to prove that those lines actually intersect. And in the third part, we have to find the perpendicular distance from a point P to the line AB. So if you haven't yet done chapter 10 in the textbook, this video is probably going to feel quite difficult because it's going to mix up those skills. But if you have done chapter 10, this should be some good revision. The first thing to notice is that we've been given position vectors to go with 4 points: OA, OB, OC, and OD. So step 1 is to find the direction vector from A to B and from C to D. Notice that when we're finding the acute angle between 2 lines, we don't actually work with the equation of the line, right? All we need to work with is the direction vector. So you can visualize that if you take your hands and just put 2 lines into 3 dimensions and ask, what does it mean to find the acute angle between them? Well, you could draw them like that, or you could shift them up and down in 3 dimensions or sideways or whatever. But what we're looking for depends on the direction vectors. It doesn't depend on the starting point for that line. Okay, so this is easier than some of you have been trying to make it. Some of you have started off by writing out R is equal to this plus lambda times this. You don't need to do that until you get down to the second question. All right, so step 1 is to find AB and to find CD. So the direction vector from A to B is the position vector OB minus the position vector OA. I'm writing these into column form. We've got 5, -2, -2. Now it's a wee bit hard to see that up there. There we are, that's better. Take away 4, 0, 1. And that gives me 1, -2, -3 for that one. And CD, doing something similar, we get OD minus OC. So that's -1, 0, -4. Take away 1, 1, 0. And that gives us -2, -1, -4. And we can just visualize it as what we're after here is that acute angle theta. Now I've drawn those in 2 dimensions, so of course it looks like they intersect, but they might not, they might be skew. Okay, so we can see already that they're not parallel, but it could be that they never ever meet, but we can still find the acute angle between them by picturing one of them as being dropped down on top of the other one. We're just looking at the direction vectors. So the next thing we're going to use is the definition of the angle between 2 vectors as being the scalar product scaled by the magnitudes times together. So in here, this is what we've got. The dot product or scalar product is very easy to work out, and that was worth a mark in here. Some of you making some silly mistakes in the denominator. So the magnitude of AB is going to be 1 plus 4 plus 9, right, from up here. And the magnitude of CD will be 4 plus 1 plus 16. That gives me -2 plus 2 plus 12 divided by the square root of, what have we got, 14 times the square root of 21. So that you can whack that into your calculator if you want to, but I cleaned it up a wee bit first, and I got, I'll just do this slowly so you can see what I'm doing with the surds. I've got 2 7s and 3 7s, so that works out to be 12 over 7 root 6. And then taking that out to quite a few decimal places, so don't round too soon here, that's cos of theta. So theta is going to be cos inverse of that if that gives me a negative, an acute angle. And in this case, it does. So that worked out to be, in degrees, 45.6 degrees, going to 1 decimal place. Now the next thing we have to do is we have to show that the lines AB and CD intersect. So this is tedious, but not that difficult. The first step is to write the equation for the line AB and the equation for the line CD. There are several ways to do this, but I've picked, for my anchor point, I've picked point A for this one because it's got a 0 in it, and I've picked point C for this one, but it really doesn't matter. So my first step here is to say line AB has got equation 401 plus lambda 1, negative 2, negative 3. And line CD has got equation 110, and I've used the parameter mu. So negative 2, negative 1, negative 4. So what we're trying to say is that if we've got an intersection, then if this is line AB, then every point on that line has an associated lambda value, and every point on line CD has an associated mu value. So we're trying to find a pair of mu and lambda that are going to give me the same position vector. Right, so we're solving to look for a pair of lambda and mu. So let's set up the equations. So we've got 4 plus lambda is equal to 1 minus 2 mu. Negative 2 lambda is equal to 1 minus mu. And 1 minus 3 lambda is equal to negative 4 mu. I'm going to work with these two, 2 and 3, and I'm doing that because I've got a nice simple thing here. Right, so you could do this by substitution. I've done it by elimination. So we're going to set up mu minus 2 lambda is equal to 1. And here we're going to set up 4 mu. I think that's right. Hang on. Oh, mistake here. Important mistake. Don't want to have that. So that's lambda there. Right. 4 mu minus 3 lambda is also equal to, is equal to negative 1. Okay, I am actually going to do substitution on this. So mu is equal to 1 plus 2 lambda, 4 times 1 plus 2 lambda minus 3 lambda is equal to negative 1. What have I got? Well, I've got 5 lambda plus 4 is equal to negative 1. 5 lambda is equal to negative 5, and lambda is equal to negative 1. Now, I'm thinking probably most of you have decided to skip through this bit of video. That's fine as long as you're getting it right. So we've got that lambda value. We now need to get a mu value. So we'll get the mu value from here. So mu is equal to 1 minus 2, which is also negative 1. So these are my two values. Now I have to go and check that they satisfy equation 1. All right, so I'm going to put them back into this one here, and I'm going to show what the left-hand side and the right-hand side are. And I'm going to say what I'm doing. Check in equation 1. Left-hand side, 4 plus lambda is equal to 4 plus negative 1, which is 3. And that's equal to 1 plus negative 1 times negative 2, which is 1 minus 2 mu, which is equal to the right-hand side. So we can say that all three equations are satisfied when lambda equals negative 1 and mu is equal to negative 1. Therefore, the lines intersect. So that's that part done. Okay, now the last part is to work with a position vector P and to show that the perpendicular distance from that point to the line is equal to root 3. So it's best to start, as you know, with a diagram. So here's my line AB, and here's my point P out here. Right, so we've got the position vector of P is 1, 5, 6, and we've got the line AB is this, 4 plus lambda, negative 2 lambda, and 1 minus 3 lambda. So we've already done that work before, so we're going to make the most of it now. We're going to draw a very bad diagram here. So we've got putting a right angle in here. Now, why am I putting the right angle in? Well, in this case, it tells us that we're finding the perpendicular distance from P to the line, right? And we're trying to show that that length from P to this point here, which I'm going to call X, we want to show that that has length of root 3. So we can find, what we can do is we're going to say, what is the position vector of X? Well, OX is a point on that line. So its position vector is this. And that means that we know what XP is. So XP is OP minus OX. So it's going to be this vector, take away this vector. It's going to be 4 plus lambda minus 1, negative 2 lambda minus 5, 1 minus 3 lambda minus 6. So xp is equal to 3. Have I done that wrong? I've done that wrong. Yep, that's backwards. Okay, sorry guys. So it's 1 minus 4 minus lambda, and then it's 5 minus negative 2 lambda, 6 minus 1 plus 3 lambda. That gives me negative 3 minus lambda, 5 plus 2 lambda, 5 plus 3 lambda. And what we've got now is we've got the vector for this, and we know the direction vector of the line. So if they're perpendicular, we have to have cos of theta is equal to 90. Right, so we're trying to find the value of lambda now. So what we need is we need xp times the direction vector, 1, negative 2, negative 3, has to be equal to 0 for cos of theta is equal to 90 degrees. Because this thing here is xp dot 1, negative 2, negative 3 divided by those two things has to be 0. But we don't need to worry about the magnitudes, right? We just worry about the denominator. So this is what I have to work out next, and I'm going to use what I had for xp. I'm writing this out pretty slowly because I'm hoping that some of the people watching are people who had trouble with this question, not the people who got this question completely right. So we need that to equal 0. So expanding all of this out gives me negative 3 minus lambda minus 10 minus 4 lambda minus 15 minus 9 lambda is equal to 0. That gives me negative 13, negative 28 minus lambda minus 5 lambda minus 14 lambda equals 0. So lambda has to equal negative 2. And now I'm ready to put that back into xp, right? Because that means I can find, I don't need to do anything except for substituting into here. So xp is equal to negative 3 minus negative 2 plus 2, 5 take away 4, and 5 take away 6. That gives me negative 1, 1, negative 1. And our job was to find the length of that. So we'll just show how we get this. We've got negative 1 squared plus 1 squared plus negative 1 squared, which gives me root 3 as required. So there you go. The angle finding skill in here is one that comes up all the time, especially now that planes has gone out of the curriculum. And so does the skill about finding the distance from a point to a line. So definitely worth being really confident with both of those two skills. Thanks for watching. Email me if you've got any questions on this or the other vector stuff.